Alright, so welcome back to our fourth installment of waves, sound, and light, and now we're moving on into light rays and rectilinear propagation. Rectilinear means to go in a straight line. Light, so a ray of light is often represented as a single arrow, whereas a beam of light is often represented as many rays. A ray of light is the direction in which light propagates. A beam of light is a stream of light energy. When light from a point source of light hits an object, a very dark shadow is produced. It is referred to as an umbra. And here you have it. Small little hole hitting on some sort of object. And then you have this very dark shadow. When light from an extended source of light hits an object, a very dark shadow or umbra, as well as a partial shadow known as a penumbra, are obtained. So when the hole is a little bigger, we call that an extended source of light. Right? It gives the light the ability to form two shadows, one very dark and one very light. That's all it's saying. Now the moon is a non-luminous body. It reflects light from the sun. An eclipse of the moon occurs when the earth is between it and the sun. So basically, when you eclipse the moon from the sun, something must be in front of the moon. And the only thing that could be in front of the moon is the earth. But the sun isn't going anywhere, it's in the center, not moving anywhere. And then, so an eclipse of the moon is referred to as a solar eclipse. Okay? So how I remember that is sun, earth, moon. So the earth is in the center or in between the sun and the moon. The sun becomes eclipsed when the moon passes between it and the earth. So in this case, when the moon is now between the earth and the sun, you have a solar eclipse, right? And so here we have an example of a solar eclipse where you have two shadows. The sun is an extended source of light, right? And you have two shadows. You have the darkest shadow where you're going to have the total eclipse, which we refer to as the umbra, and then you have the partial shadows that people not directly in the area of the total eclipse would experience a partial eclipse, right? And that is actually the penumbra. And then those people that are outside of the umbra and the penumbra wouldn't see any eclipse at all, right? So it always depends on which part of the earth is exposed to the solar eclipse at any particular time. And as you can see, it's here nicely explained. At point A, there'll be no eclipse, or the eclipse is happening, but if you live in region A and E, you won't experience an eclipse. If you live in region B and D, you are going to experience an eclipse. It's only going to be partial. If you live in region C, you're going to experience a total eclipse, full-on eclipse. Now, when an object is placed in front of a pinhole camera, a focused, real, and inverted image is formed on the translucent screen. And you should really go and try to make a pinhole camera. It's not as easy as it appears here. I'm gonna put up a video. You should see it right now. I'm gonna put a link to one of the videos where I use in class to build a pinhole camera. It's a lot of fun, and maybe you can try it too when you do get a chance. Okay. Alright, so comprehension: define a ray of light, define a beam of light. So again, define a ray of light. So a ray of light is the direction in which light propagates, and a beam of light is a stream of light energy. State the property of light responsible for the formation of shadows. The fact that light travels in straight lines is the property of light responsible for the formation of shadows. It doesn't go or bend corners. Yeah. So draw ray diagrams to represent the formation of each of the following: the shadow produced by a point source of light, an eclipse of the moon, and an eclipse of the sun. So these are things you can actually do. You just go back in the notes and you could do this. Okay, so just go back in the notes and you draw the angles here. So you have the eclipse of the sun, and the other one is the eclipse of the moon. Okay, so you can do those drawings on your own. Red diagrams to show the formation of the image in a pinhole camera for each of the following cases: the camera focusing on an image of an object, the effect on the image of increasing the size of the hole, the effect of the image of moving the object further from the camera, and the effect on the image of making the box deeper. So you could try all of that. I'll make sure what I would like to do is to build the camera itself, and then you could answer these questions. Okay, reflection and refraction. There are two laws of reflection. Law 1, the incident ray, the reflected ray, and the normal at the point of incidence are on the same plane. And law 2, the angle of incidence is equal to the angle of reflection. The image you see in the mirror is called a reflection. When light hits the surface of a mirror, it bounces away from the normal at the same angle the incident ray did. Images formed in the plane of a mirror are: 1, the same size as the object; 2, the same distance perpendicularly behind the mirror as the object is in front. So if the object is 5 meters away from the mirror plane, then the image is 5 meters away from the mirror plane. It is virtual, meaning that it's not real, and it's laterally inverted, just like the picture you see below. You see the mirror, so it looks like it's backwards. So again, virtually means not real. The image cannot be formed on a screen, and light does not come from where the image appears to be. Laterally inverted means reversed side to side, so that the image of a word placed to face a mirror is reversed as shown. So reflection ray diagrams using point objects. So usually when I do this practical with kids, it's very hard for them to grasp. So I don't really do it anymore, because I think they're just doing it because I tell them to do it or come around to show them. So I don't really do it. I think it would take years for them to grasp it, because they don't have any idea what they're looking at. And sometimes I go back in my mind to when I was their age, and I remember doing this lab and thinking, what am I looking at? What's the teacher seeing? So I think this is a lab for older kids, much older. No matter how you explain to kids, look at the pin and look at what's there and look from an angle, they won't get it. So just save yourself the trouble. Go with something much simpler. Start with reflection, and if you're going to do a refraction type lab, if you do reflection, don't do it with the object. Do it with normal, like a ray box, and you just let the ray be reflected away from the normal. So it's easy. So you would have, let's say you have a line, that's the mirror plane, and you tell the kids to draw a perforated line or dotted line there, label it as a normal, and they could already pre-measure the angle of incidence. Remember, the angle of incidence is always between the normal and the ray itself. It's not between the ray and the mirror plane. It's always between the normal and the ray. Okay, so they could pre-measure the angle of incidence, so we call that theta 1, or angle of incidence. And then you could get a ray box to be shown on this line itself, so you get a red box with light in a straight line to shine it along this line, and then that light will bounce off the mirror and go at the same angle, will be reflected away from the mirror. And this is what they understand most. This is what students understand most. So just keep it simple so they could grasp the concept. This actual experiment is really for children to, or students to see or prove that the image form is the same distance away from the mirror plane as the object, right? And more than likely, it's better if you demonstrate it to them without them doing it, because honestly, it's very hard for them to grasp at that tender age. Usually older students get it. Older students get it, but the younger ones, 15, 16, not so much. Alright, so there are two laws of refraction. The incident ray, the refracted ray, and the normal at the point of incidence are on the same plane. And law 2, the ratio of sine theta 1 over sine theta r is a constant for a given pair of media, where I is the angle of incidence and r is the angle of refraction, and this is referred to as Snell's law. And here we have it. So the figure, I took this out of a textbook, I think it was a physics concise text. The figure 24.8 shows the type of diagram that is helpful when tackling a refraction problem. And here we have the angle of incidence. We have it here. Angle of incidence right here. And then we have the angle of refraction. So it shows that light, once it moves from a less dense medium, in this case air, once it moves from here and goes in a more dense medium, you have greater refraction, meaning bending bending closer to the normal, right? So this is the normal here, by the way. This is the normal. So refraction means you're going to be bending closer towards the normal, and so the refraction is greater in this denser medium, and that's what it's showing you. Now, how is it related? You can actually solve for the refractive index of any material that's transparent, right? And I'm not going to go too quickly into that, but the relationship is such that the refractive index 2, which is of the material, divided by the refractive index of the air, equal to sine theta 1 over sine theta r, equal to the speed of the incident ray, the light of the incident ray, divided by the speed of the light that is being refracted. So the incident is all in the numerator and refracted in the denominator. And then for determining the refractive index of the glass, which is specific to any substance, so we're going to get into that later too. So it's specific. Okay, you could actually use the refractive index of transparent material to determine what the material really is. Is it plastic? Is it perspex? So perspex, I think, is plastic. So you could determine the type of plastic. That thing people put on the nails. I can't even remember what it is. I can't remember what it is. What do people put on the nails? It'll come to me. So yes, whatever you put on your nails, you can actually determine if it's real, you know, once it's hardened, all of that. So that's how it's related. So for light traveling from one medium to another, the ratio sine I over sine R is the refractive index of the medium relative to the first N2 over N1. So that's refractive index to which is the substance over that of air. For light traveling from one medium to another, the ratio of speed in medium of incidence divided by speed in medium of refraction is also equal to the refractive index of the second medium relative to the first. So they're all interrelated. You could solve for one. You could solve for one. Like you see how it is here. If you're given a question that only gives speed and the angles, you could ignore this part and solve using these four. If you're given a question that is missing speed, you could use this and solve. You could use 4. So once you have, you know, you saw the related, you could use only you could use 4. Really, truly, you only need 4, right? But they're showing you how they're interrelated. So here, this is what I meant by the as specific. The refractive index of air is 1. And please note that refractive index doesn't have any units, it's dimensionless. The refractive index of water is 1.3. The refractive index of glass is 1.5. So behavior of light when passing from one medium to another. When light enters a second medium perpendicular to its interface, it does not deviate. The angles of incidence and refraction are both 0, so it doesn't bend. So once it's 90 degrees, so as it's a perpendicular, 90 degrees meaning that this is 90 degrees here. Sorry, let me just get rid of this. So once light so this one is going out and this one is going in. So once it's 90 degrees, there's no deviation, right? So 90 degrees, no deviation. So this going in and this coming out, no deviation. 90 degrees towards whatever, no deviation. Its speed is greater in the less optically dense medium, and we did that as an experiment. I think, yes, I don't think it is there. The refraction lab was taped, and it is up there for you to see. And the calculation showed that definitely one, it was 3 things we were trying to determine. But of the 2, we saw that light bends once it goes from a less dense medium to a denser one, and that light actually slows down when it goes through a denser medium. When light enters a more optically dense medium other than perpendicularly, it refracts towards the normal, that is, the angle between the ray and the normal decreases, and its speed also decreases, which is what we observed. And it was a really good lab. You know, we could do so much more with that lab, but given the time that we were given, you know, anyway, that's a whole different story. When light enters a less optically dense medium other than perpendicularly, it refracts away from the normal. That is, the angle between the ray and the normal increases. So when you're going from denser to less dense, the refraction is not so great and its speed increases, which obviously is the opposite. So when you're going from less dense to denser, you have slow down, it slows down and it refracts more. When you're going from denser to less dense, it refracts less and it speeds up. Makes a lot of sense, right? Now, examples of refraction ray diagrams. So basically it's showing you when you're looking at an object that is underwater, it appears closer to the surface than it is really, than it apparently is, because of refraction of light. So it's like a trick. Light plays tricks on the eyes, and that is why when you're standing in a pool, you look so distorted. Your legs look like they're up here when they're really at the bottom. So it's due to refraction of light. So when we're doing labs or practicals based on refraction of light traveling through a glass block, you see here the incident ray along the normal, and then you will see it refracting towards the normal and then exiting. Now they all have names. The light at different points of its refraction all have names. So the ray at the beginning is referred to as the incident ray. The ray that is passing through the block and has refracted towards the normal is known as the ray that is known as the refracted ray. And the ray that is now leaving the block is known as the emergent ray. Okay? So it's known as the emergent ray. The following equation may be used when tackling a refraction problem, which is the same one we were looking at earlier, right? So all of them are interrelated. The dispersion of white light, so we're on to dispersion now. The dispersion of white light is the separation of white light into its constituent colors. The figure below shows the setup of an experiment originally done by Newton, and basically what Newton did, where he discovered that white light was made up of 7 colors. RGB: red, orange, yellow, green, blue, indigo, and violet. And he found this out by using a prism. And the prism was able to separate this light, which was shown up on this visible screen, right? And from there, what he did to prove that white light was only made up of these 7 colors is separate them using a slit, as you can see in figure B. And he used another prism to see if that red light would then further separate out into different colors. And the light that came out was red on a white screen, so it did not break apart or separate again. And then he recombined the colors by flipping the prism to show that all of them will converge to produce white light again, right? So he went all out to prove that only 7 colors make up this white light. And at this time in our life, it's still the same idea, that only 7 colors make up this white light, right? And using prisms and breaking up the experiment to prove that it's only white light, he showed that when they're separated, it made different colors from white light to these 7 colors. And when you flip the prism, what they did was recombine to form back this white light. So he was happy with his experiment. It proved what he wanted to prove. Newton was he was out there. So Newton made a number of changes to the experiment in order to prove that the origin of the colored light was not within the prism. He, 1, changed the size of the slits of the collimator. 2, used prisms of different types. 3, isolated a color and showed that it was not affected by another prism. 4, he altered the distance between the light source and the prism. And 5, he added a second prism to show that the light colors can be recombined. So he did 5 things to prove that white light was made up of 7 different colors. You come up with a new experiment to show that more colors are within white light, and you win a Nobel Prize. Pretty sure you will, right? So the critical angle and total internal reflection. When light passes from an optically denser medium to one which is optically less dense, it will have a large angle of refraction. At a certain angle of incidence C, the refracted ray passes just along the surface for angles greater than the critical angle. There is total internal reflection. So that means that light is not going to leave the material, right? The critical angle may be defined in 2 ways. The critical angle of a material is the largest angle at which a ray can approach an interface with a medium of smaller refractive index and be refracted into it. The critical angle of a material is the smallest angle at which a ray can approach an interface with a medium of smaller refractive index and be totally reflected by it. So here we have some pictures for you to see what I'm talking about. The ray must approach the second medium from one of greater refractive index, that is, from one in which its speed is less. The angle of approach must be greater than the critical angle. So here we have maybe some light passing through some glass, right? And it's leaving, and as you open out the angle, you realize that the angle of refraction gets wider and wider and wider. So it's not so bent, it's not so bent, and it's moving towards the barrier right here, which is the glass barrier. Eventually, this is the critical angle. The critical angle is where you have the refracted ray being 90 degrees to the normal, right? So this is the critical angle. and then the total internal reflection happens once the critical angle is surpassed, right? So the critical angle is where the refracted angle is at 90 degrees to the normal. So there is no more refraction happening. It's just at 90. Well, there is refraction, but this is the angle at which just before the total internal reflection will occur, meaning that light will no longer be able to leave the substance. It will now be trapped inside of that substance. Alright, so I hope you understood what was taught just now, and we're going to move into the the fourth installment, which is the Mirage. See you later!